Okay, getting started with Chem 3A, how science works. This is our chapter 0. Very short, we'll probably even bust into chapter 1 today if we're lucky. Sand can be annoying because it is so small and it is coarse and rough and irritating and it gets everywhere. Just like all other ordinary matter, sand is composed of little tiny particles, really, really small particles, unimaginably small particles, called atoms. Neither I nor you can imagine, probably, how small they are. If you can imagine how small atoms are, congratulations. You've done what few before you could have done. And I certainly can't. I don't feel like I've got a good innate sense of how small atoms are. A single grain of sand, one of those really tiny, annoying little grains of sand on the beach, if you pulled out all of the different atoms and counted them all up, there would be more of those little atoms than there are the grains of sand on the largest beach in the world. So imagine walking up and down like Pismo and Avila Beach, how long it is. It takes you a long time. There's tons and tons of sand there, and there's more atoms in one grain of sand than there are on that beach or even bigger beaches. And this is one of the great scientific discoveries of humankind. Another thing often associated with sand, water. We'll be looking at water a lot. It shows up all over the place, partly because we drink it, partly because it just has some really fun and unique properties. If we want to understand how matter behaves, matter like water, like sand, like glass and crystals and other things, it's important that we understand how the particles that compose that matter behave. If you want to understand how a sports team is going to do in the playoffs, it's important that you understand how the players on that team behave. Where do they excel? What are their weaknesses? And how do those match up with the other team? And that'll give you some idea of how that team is going to behave in the face of adversity playing that other team. All matter, anything that has mass and takes up space, so all of us, the desks, even the air, is composed of both atoms and molecules, or at least one of them. And we'll get into some of the distinctions between these things. Molecules are groups of atoms bound together with chemical bonds. We'll get into those also later. If we were to draw up a theoretical diagram of, or image of what a water molecule looks like, representing different atoms as different colored spheres, we might come up with this hypothetical linear water molecule. In actuality, from testing and observation, we know that it has this bent shape. This might not seem like it makes a big deal, like it's a big, important thing. Because of the way that water is having this bent configuration, life exists. If water existed in this linear fashion, life would not exist. We wouldn't be here. It would change so many things about the way that the world is. Just that little tiny change of hydrogen atoms up or hydrogen atoms down, or whatever orientation you want to imagine. So a lot of really tiny little details that actually make a really big difference. The world that we experience actually has a lot of chemistry in it. One of the things that I really like about this class in particular is that we don't go super deep into the weeds with some of the math stuff, some of the real minutiae, real heady stuff, but we cover a lot of material, and so there's a lot of opportunities for me to share with you ways and opportunities and places that the chemistry, the science that we're learning about actually shows up in our real lives. And there's some applications, some things that we can take away from what we're learning in class that'll actually help us in the real world, or at least make us look smart in front of our friends and family, in rare circumstances. So that connection between the atoms and molecules and the world we experience every day is part of what we're learning about, what we're exploring in this chemistry class. Everything, all the things that you can hold or touch, is made up of things that we can call chemicals. It encompasses all of it. They make up pretty much everything that we come in contact with. Things that aren't chemicals are like light, and other forms of electromagnetic radiation. But for the most part, it's all chemicals. The popular conception, what you often hear in the media, there's this conflation of chemicals equals dangerous chemicals. And not all chemicals are dangerous chemicals. There are also perfectly fine and good and safe and healthy and beneficial chemicals. It's just that a lot of what we hear is chemicals used as bad chemicals, harmful chemicals, things like acids and bases and other solvents that might be in these glass containers, and then like raw sewage or something. It's probably just water effluent, but that could be a representation of raw sewage getting dumped in the environment. Those would be examples of chemicals where they're not supposed to be, or chemicals that are bad within their context. So hopefully we can break some of that down. Ordinary things are chemicals as well. The water we drink, the air we breathe that we need to live, that our fish need to live. The food we eat, like pizza, love pizza. The medicines that we take to help us get well, or just not be in pain, or function like normal human beings, and our bodies. These are all examples of chemicals. Does anyone have any clue why I chose pizza for this picture, other than pizza's yummy? There's lots of other yummy foods.
Yes, food has a lot to do with chemistry.
Food does have a lot to do with chemistry. There's a particular memory that I have of going to, when I was in grad school, Blaze Pizza up in UC Davis, in Davis. And Blaze Pizza, I don't know if they still have it, I haven't been back, but up on the back behind where all the people are taking your order and making your custom pizza, no chemicals ever. And that's bugged me enough that years later I decided, let's put pizza in there, because it's not no chemicals never, or no chemicals ever, it's yes chemicals always. It's all chemicals, the pizza's the chemicals, I'm gonna eat those chemicals and they're gonna taste good. So that's my little grudge with pizza. If you like Blaze Pizza, that's perfectly fine. They have a good hot sauce, or spicy red sauce. So we're interested in why the world is the way that it is. I probably won't be this high energy and manic next class, so I'll tone it down a little bit. Just first day of class jitters. You may have learned this in elementary school, the scientific method. We're going to cover it briefly because it's in what we're supposed to teach you. It doesn't really, I feel like, play a huge role in the course, but it's a good idea to understand kind of the process that chemists use, that most scientists use when they are doing research, when they're trying to solve problems. It's the scientific method. And it's not really used super strictly necessarily. There's often some fluidity, but until you've mastered the game, until you've really learned how to use the scientific method, it's a good idea to play it nice and safe and strict. And then once you've learned the rules, once you've mastered the system, then you can sort of break the rules, and that has meaning and value to it because you already know the rules. So the scientific method focuses on observation and experimentation. This is different to what I believe was the ancient Greeks and Romans maybe, where they very much emphasized logic and reason. Like they just kind of thought about stuff. And so this is very different because they were actually like, let's try doing stuff. Let's make a guess and then let's actually try something instead of just sitting around and thinking about it and drinking our poisoned wine. So the 4 key characteristics of the scientific method are observation, formulation of hypotheses or a hypothesis, an educated guess, testing those hypotheses with experimentation, and possibly formulating laws and theories. I think educated guess is probably the most popular definition people know for a hypothesis. And if you didn't write those down right away, they are showing up on these next slides. So here's one diagram. This is one from our book online of what the scientific method might look like. We would start out with an observation. We notice something. That's all there is to it. We notice something. We see something. We don't say something. We just see something. And then we, maybe because of the observation that we made, we come up with some guess. Why was the thing that we saw the way that it was? What about it was special? Was there something interesting about it? We maybe make a guess. This was this way because of, I don't know, like, why was there pee on the countertop this morning? This isn't a real life example from me recently, but it probably happened when I was a kid. I wasn't the one doing the, Anyway, observation, there's pee on the kitchen island. That's the observation. The hypothesis, someone, probably a young person with a proclivity for climbing on things and peeing on things, peed on the countertop. The experiment might be set out a trail cam, set out a camera to catch them in the act if they do it again. If this is a recurring, event. And then we could come up with some silly laws and theories about why that happens. Maybe, little brother had ice cream after 10 o'clock. Every time he has ice cream after 10 o'clock, it does something to his brain and he just has to climb up on that countertop and take care of business. I don't know, some silly examples. So again, our first step is an observation, or it could be a measurement. Sometimes these are made with the naked eye. You don't need anything other than your senses, your eyes, your fingers, your sense of smell. Others rely on the use of sensitive and oftentimes expensive, that's just a side note, instrumentation. You might need $500,000, $1 million worth of sensitive instrumentation and the skills and know how to use them to make some of these observations. But it's going to involve some measurement or description of some aspect of the world. A historic example of this, Antoine Lavoisier studied combustion. He took closed containers, like big tubes. You can see the big tube that he's got on his desk here. Put a big tube, put some stuff in it. Let's say we're burning blue logs. I don't know where we got these blue logs from. The blue forest, I would guess. And we light them on fire in a closed container. Most of you probably know that fire is not going to stay out or stay on for very long. It'll probably burn up, choke itself off before it can burn through these blue logs. But then after we've burned this, let's just say that we had a really good flame. We had a lot of oxygen in the chamber. I just erased the whole thing. Let's bring it back. At the end, we have just all this blue dust. We completely successfully burned it, only blue dust. That's not particularly interesting, but what Lavoisier observed was that before and after burning, since it's a closed container, the mass didn't change during composition, or during combustion, sorry. So we weighed it before with the blue logs, we weighed it after with the blue dust, and it was the same mass, even though we very obviously have different things. And what was some of the takeaways from that? There was a hypothesis that was generated. That hypothesis being that combustion involved combination with a component of the air. So that was a guess. We could have proved that wrong. Remove all the air from the container, perhaps. And great, it is in here, what I was leading up to. So after coming up with this hypothesis, did some more experiments, more burning stuff. In the case of Lavoisier, did more trials of burning blue logs, maybe burned green logs, maybe burned yellow logs, whatever color logs you can imagine, burned them up in the container to figure out if his guess was correct. If this happened every single time, could have come up with more hypotheses. If, however, it turned out that burning orange logs, it doesn't stay the same mass, then that might disprove the hypothesis. There may be something worth looking into about orange logs. And so we could revise the hypothesis and test our new hypothesis again. after all of this burning stuff, which honestly, like, nice job, fun job to have, just burn stuff in containers. After all of this, Lavoisier said, every time I do this, it comes up with the same result. It's the same mass in the container. Lavoisier developed what we call a scientific law. This is a statement of what happens. It's a summary of what happens. So if I burn any logs in my closed container, the mass is the same after the logs are done burning, for example. So then if somebody else went and took some new color of log, fuchsia logs have entered the scene. Somebody says, I've got fuchsia logs. If I burn them in the container, the mass should be the same based on this law. Even though nobody's tested it, we know based on all the other logs that we've burned in these containers, it's been the same mass before and after. So if we burn the fuchsia logs, we would expect the same thing to happen. So we can kind of apply it a little bit outside of just what we've observed. And we can test that as well. From all of this, Lavoisier developed one of the important things in this set of slides, the law of conservation of mass. So I'll go ahead and box that in for you. The law of conservation of mass, we've got a couple of conservation laws that come up in the class. In a chemical reaction, like burning stuff, matter is neither created nor destroyed. So since it was a closed container, none of the smoke, the particles that were produced from the combustion were able to leave the container. They stayed in the container. That's why it was the same mass. We rearranged the particles. They weren't actually destroyed. We didn't create new particles. Even though the appearance changed, everything that we started with was still in there. And so the mass stayed the same. And this is a very important law for chemistry. Another thing that might rise from a couple of well-established hypotheses, a bunch of guesses, they all come true, is that we might get a scientific theory or a model. And the way that a theory is different than a law is the theory gives us an explanation. It gives us why something happens. Not just what happens. So why was mass before and after different? The law of conservation of matter says that it will be different, or that it will be the same, sorry. The before and the after, those will have the same mass. It doesn't tell us why that happens. It doesn't explain the underlying cause, the underlying mechanism that I sort of talked through. It doesn't explain that. So it's a law. A theory explains why it happens. And these can be used to predict behavior as well, but we can use them with extra conditions, extra circumstances. They get a little bit broader reach. So Lavoisier's law led to John Dalton, another important figure in science. It led to his atomic theory. The atomic theory is the idea that all matter, including pizza, is composed of small, indestructible particles called atoms. So if you had an infinite time on this earth and a really, really sharp knife, you could chop everything down one slice at a time until you got down to the atoms. Some of this stuff will come up again later. So comparing our law and our theory, again, the big difference is that a law states what happens, and our theory tries to explain why things happen. They can both arrive or arise from observations and hypotheses. They can also both be proven false, but a theory is a little bit better because of that why part. It's a little bit better. Any questions so far? Again, this is a short chapter. We're basically done. Confusion? Comments? Great. And then here's our inspirational quote. Not all the chapters have inspirational quotes. It's just chapter 0 that has this fun quote. So this is a quote from Hoffman, 1981 Nobel Prize winner for chemistry. I like the idea that human beings can do anything they want to. They need to be trained sometimes. They need a teacher to awaken the intelligence within them. But to be a chemist requires no special talent. I'm glad to say anyone can do it with hard work. Any one of you, even if you've been really bad at science, at math in the past, you can succeed in chemistry. Part of my goal, part of why I like teaching is I want to help you succeed in chemistry. I obviously can't force you to be good at chemistry. There's a lot of onus on you to put in work, effort, spend time thinking about it, reviewing material for you to succeed. But part of my job is to help facilitate you being passably good, at least at chemistry. So that'll do it for chapter 0.